So this section here is going to be building off of kind of what we did with the sine cosine stuff, except for now we're just going to do it with the tangent stuff. So that first chart there starts off very similar to what we had in our sine cosine stuff, where we got like our domain, range, x and y intercepts, and that kind of thing. So for the domain of this, for when it was sine and cosine, it was all real numbers because it can go both directions, right and left, forever. The tangent ones, we're going to have some points of discontinuity, like asymptotes or spots, basically, where it can't be those values, because when we do some of the tangent ones, since we're doing sine divided by cosine, anytime our cosine is 0, it's always going to be a point of discontinuity, because can we divide by 0? We can't, right? So because we can't divide by 0, there's going to be some holes in our graph, which you'll see when we graph it out, and that's why this is kind of weird there for the domain. Range then is the one that it's all real numbers, because you can go up and down forever with those numbers. Y-intercept's always going to be 0. X-intercepts are always going to hit at the spots where it's multiples of pi, so like 1 pi, 2 pi, negative 3 pi, that kind of thing. And then our graph is going to end up being an odd function. Okay, so let's actually, I don't know, you want to graph it out now or you want to wait till the end to graph it out?
No.
Now, okay, let's graph it out now then. So, grab your packet thingy from yesterday we were working on, and the back page should be tangent. And we're just going to go through there and graph that stuff, same as what we did yesterday. So when we're doing this, again here, like your 30s and 60s aren't marked in. So like a space and a half in front of the 45, same as yesterday, would be our 30. And then a space and a half behind the 45 would be 60. And then again, there's nothing around the 90. Around the 135, a space and a half before it is, was that 120? Space and a half after that would be 150. And then nothing around the 180. Around the 225 should be a space and a half in front of it is 210. Space and a half behind it would be 240. Nothing around the 270. Around the 315. Space and a half in front of it would be 300. Space and a half-ish behind it would be 330. So those numbers are the same as yesterday. Okay, and then again, same as yesterday, we'll just go and graph those points that are in those tables below. If there are errors in it, just let me know. I tried to just copy and paste, so I wasn't doing a whole bunch of stuff. But if there are negatives and stuff missing, just let me know, because I might have made mistakes like yesterday's one. So, but just graph those out. Like 0, 0 is the first one, then 30, 5.77, so just a little bit above the half. 45 is at 1. And I'll just let you guys graph those out like you can. The 60, though, when it's like 1.7 or whatever, just kind of eyeball where you think that would be, because it'll go a little bit off your graph. But just kind of eyeball that in there. And I'll let you guys graph those. When you get to ones like the 90, it's the empty set sign where it's the 0 with the slash through it, because it won't work at 90. That's one where our cosine value is 0, so it's not going to have any points there. So you can just like skip over the 90, and also like the 270, there's nothing there. But all the other ones should be stuff we can graph. after you get it graphed, I'm also going to go and highlight or mark in a little different here my like asymptotes or my points of discontinuity. So like the 90 would be one of those because we know it can't hit at 90. And then in the chart, I'm just going to make that like the same highlighted color just so I know why I had that line there. And then the same with the 270, I'm just going to show that it can't hit on that line either. And then highlight again the 270 just in that same thing, just so I can see those spots there. But I did it in a different color, that way I don't think it's part of the graph, but just showing that it's not going to hit those spots. And then I would also do like we did yesterday and make your tiny little graph of what the actual tangent function looks like on both sides, in the positive and the negative. So like, should be just those little like S shapes there. And if I go make my little marks here, so like 1, 2, 3, 1, 2, 3, it shouldn't cross over this first mark here when you do it, so it's kind of like getting close to it, but not going to touch it. And then same with this negative one there, like the 90. It's going to get close to it, but won't cross it. That wasn't a great line, but you get the gist. And then we skip over that one, and then your next one, the center, is at the second tick mark there, and it's going to get close to that third line, but not cross it. Same thing going back the other way. And then again, you'll skip that or the first line there, go to the second one, and it'll be coming off of that one. And kind of going back down to that one, just so you can kind of see what it looks like, you know, over more of a chunk of a graph. Okay, cool on that? Alright, so let's get back into the theorem-y stuff here then. So I don't know, I don't have a clue how to pronounce that. Periodicity? I don't know, whatever, theorem, period theorem. So with that, basically what this is going to be used for, so it's got for any real number x and any integer n, and then it gives a bunch of formulas there. The formulas are similar except for the tangent one, instead of it being 2 pi and 360, they switch it to pi and 180 because we know tangent's got some different stuff in there. But basically what that's going to do is it's going to help us figure out what our values are going to be for numbers that are like really big. So like say they gave us like sine of like 4,000. Well, do we know what sine of 4,000 is off the top of our head? Probably not, but what we can do is we can use that theorem and the concepts of it to figure out what that sine of 4,000 is compared to like what it would be like on a normal unit circle. And one of the examples we do is going to be on that, so we'll use that in a bit. And then definition of periodic or period there, or and period. So function f is periodic if there is a positive number p such that f of x plus p is the same as f of x for all x in that domain. And then whatever the smallest p value is, that's what they call the period. So basically what it is, it's very similar to like that cycle thing that we had the other day, where it's going, you know, wherever the pattern's repeating. It's just whatever the period number itself is the horizontal length of that. So like, I don't know exactly what number it's at here and here, but whatever that distance is from like one to the next would be considered the period. And I usually, if I have to like find it or whatever, I usually find like one of the maximums and then go to the other maximum number, kind of like they have marked out here, so you can kind of see, okay, it's from this spot to this spot, or it should be the same distance if you did that for the median or minimums. So if I went from here to here, it should be the same distance as it is there from there. But it's basically just wherever the pattern is repeating, the length of that is the period. Okay, so the rest should be on our example sheets. So grab those out, and we'll walk through those. So first one here, they want us to do, consider f of x is equal to cosine x, and they want us to start by giving the domain and the range. Okay, so we did cosine stuff yesterday. What was our domain for our cosine stuff from yesterday? So what can we have for our x values for cosine? All real numbers, right? Because it can go forever right and left in either direction. So I would go all real numbers for our domain. And then range-wise, this is where we have our limitations a little bit. Where's our range going to fall on just a normal cosine graph? From what number to what number? -1 to 1, right? Because our lowest number we can have is -1, highest is 1. So it would be -1 is less than or equal to, and then I'm going to put it as f of x as our middle thing instead of y, but we know f of x is the same as y, but they just use it in function notation. That's why I did that. Less than or equal to, and then our top number is 1. And that should be in our notes from yesterday in that chart. And then for part B of this, we're supposed to figure out if our function there of cosine x is odd, even, or neither, and then justify it. And when we justify it, we'll use the stuff we did from last chapter when we figure out if it's odd or even. Okay, so cosine function in general, looking at the graph of that, is our cosine function. So this one, what do we think? Is that in general odd, even, or neither? That should be even, right? Because our even ones are our ones that can fold over that y-axis there. So if we fold it over, it should be the same on both sides, right? So we know it's even. And then the tricky thing is here is proving that it's even. So what you would want to do is you'd want to look back to your notes where we did the even and odd stuff. And in that, if it is an even function, it should be like our f of the opposite of x kicks out the same thing as our original f of x. So that's like our notation that we had for the even stuff from last chapter. So now if we're thinking about this in terms of like our function here with the cosine, how it would be written is it'd be like cosine of negative x is equal to cosine of x. And we're just figuring out, okay, is that actually true or not? So if we put the opposite cosine value in there, does it kick out the same exact cosine value as what we had before? This is actually one of those theorems we did the other day. Anyone remember what theorem it matches with? It is the opposites one, yes. So because of the opposites theorem, so you could just put that, and you could just put like by opposites theorem. So by that opposites theorem, it says straight up in there that if you've got like cosine of x, it's equal to like the opposite of your x there for cosine. So by that, it shows us that it matches with that, so it's even. And I don't think I'm going to ask anything like that. I might ask you if it's even or odd, but I don't think I'm going to make you do the proving stuff like we did last chapter. But this next one here, I am going to put one of these on the quiz, so maybe star this one because I'm definitely going to put one of these on the quiz. I'm making the quiz currently, so I'm going to throw one of these on here. Okay, so we're going to use that periodicity, or however you say that word, theorem, to find sine of 15,780. So instead of just typing that into the calculator and seeing what it kicks out, they want you to show that with this theorem, like it's going to kick out whatever answer. So we're going to use the sine part of that theorem, and we're going to use the one that's in degrees versus radians, because it's in degrees there. So the sine one for that theorem was sine of x is equal to sine of x plus n times 360. And basically what you're trying to figure out there is how many full circles it's making. That's your n number, so like how many full 360s it's making. And then the x is how much you go over 360, so how much further you're going around the unit circle past doing full loops around. So what I would do here is I would take our total number there, that 15,000 number, divide it by 360 to figure out how many full times we go around the circle. So if I divide that out, 15,780 divided by 360, I get 43.83, and the 3 is repeating. So what that tells me is I'm going 43 full times around the circle, and then I'm going 0.83 past that. Okay, so what I would do here then is that 43 is like our n value in our formula here. So like sine of whatever, that 43 is that number that we took times 360 to get like, full times around the circle. What we need to figure out now is how much further we're going. So like that 0.83, what that would convert to in like degrees. What I would probably do is I would probably figure out how many degrees I've fully gone in like 43 full times around, and then take that number minus my original number to figure out how many more degrees I have to go. Okay, so I would do that number there, that 43, times 360, because that'll tell me how many degrees I've gone around in 43 full turns, which I got 15,484, not 4, just 4,480, I don't know why I said a 4 at the end. So that's our full turns around, so that's getting us, back to our 10 or whatever that we started at. Now to get this 0.83 around, what I would do is I would just take my original number, that 15,780, minus those for the full times around, 15,480, which is 300. So that tells me that this rotation here, moving it around that many times, is the same. It's going to end up in the same spot as if I just moved it to the 300 degree spot. Okay, so that 300 degrees is what would be in there for the x. So sine of 300 is the same exact thing as sine of that big number there. Follow me so far? Okay, so if we can figure out what our sine of 300 is, that'll kick out the same answer as sine of 15,780. Okay, so sine of 300, that should be one on our unit circle, right? I don't know where my unit circle's at. We got their unit circle? Mine is not up here. Sine of 300. We'll just say it. Negative 3 pi over 2? What is it in, yeah, so sine of 15,780 would be the same as negative square root of 3 over 2, you said? Yep. So that would just be showing that using that theorem. Now, if you did that sine of that number on the calculator, it should kick out the same exact decimal as this. But like I said, there's going to be one on the test where I write it like this, where it says use that, periodicity or whatever theorem to do it. That's your setup from that. Okay. Cool on that? Okay. All right. Last one here. We got graph below, shows average travel time from downtown Metropolis to Metropolis International Airport during a typical week, Monday to Friday. For this function, determine each of these things. Okay, so we got to find our maximum, minimum, range, and then the period of that. Okay, so maximum and minimum, we're probably going to have to just estimate a little bit here with some of those values. But what do we think approximately for like our maximum? For like 47-ish. Okay, so if we go max, approximately 47, and that would be in minutes, right? So maximum approximately 47 minutes, and then what are you thinking about for the minimum?
7.
Well, it's above the 10, so I wouldn't go 7.
Oh,
17 or 16, either of those would be fine. I heard 17 first, so I'll go with that. So about 17-ish minutes. Okay. Part B then wants the range, so how do we find a range of numbers based on those numbers there? Yep, subtract them, right? So we would just go 47 minus 17, which would be 30. So our range would be approximately 30, and would be in minutes again. Or if you use 16, 31, or whatever numbers you used, you just subtract them. Okay, and then our period here, so technically the pattern's not 100% repeating itself because it's real life numbers, so like it's not going to be exact. So kind of depending probably on what day of the week it is, if people are, traveling more on Mondays or Tuesdays or whatever days. But in general, we'll just figure out what the period is. So basically we're going from like one spot where like our pattern starts to like a spot where our pattern stops. So like say I go from like that spot there where my first spike is kind of starting to pick up there, to then it looks like here this is kind of where my pattern is ending. And again, you could do that for any chunk of that graph, but I'm going from kind of like, looks like it's like a little bit after 12 a.m., the first line after 12 a.m., and then the first line after 12 a.m. there. So if it is the first line after 12 a.m. and then also the first line after 12 a.m., how far would that be between those numbers? 24 hours, right? So basically a full day would be our chunk of time there where that pattern picks up. And if you think about that logically, doesn't that make sense that each day the pattern's probably going to be similar? It's probably like some of these times that's probably when people are going to work. That's probably the middle of the day, probably when people are going home from work, and then that's at night, not as many people traveling. That's probably what those things stand for. So yeah, I would say approximately 24 hours for our period of that where that pattern's picking up. Okay. All right, so that should be it. So you got that book page 255, 1 to 13 for Monday. Okay.